Swayam Prabha. Digital India. Educated India.
So what I'm here to talk to you about are a few things that we have learned from simulations. And for this particular lecture, I'll try to focus on adsorption as a process, not necessarily talking about adsorption in a process, but at a molecular scale, what matters, what we have learned, and what are things that possibly we need to keep in mind when we're designing things, or when we're designing materials, or when we are trying to understand the process in itself. And the overall program is looking at CCU and or CCUS. So in that context, slide changer works on this. Otherwise, I can use what? Yeah. So just to give you a perspective, what I wanted to show is two aspects, both for CCU. One is capture, and for catalytic utilization. Catalytic utilization primarily revolves around using CO2 as a feedstock and chemical reactions, and the capture part of it typically is done with amine solvents, but there is a lot of interest looking at capture with adsorbents. Both of these, if you look at adsorption as a process for CO2 capture and separation, or CO2 utilization, which is a thermocatalytic process which I am going to be talking about, adsorption, desorption processes are critical. So what I am just showing here is something that most of you would have seen, and this is a representation of a container with a gas. These spheres represent gas molecules, and what you see as the bottom here is a representation of the catalyst. What you're seeing here, these spheres are all gas molecules. So you have adsorption, you have surface diffusion steps, which not relevant for this particular talk. You have surface reaction steps. Again, there's a change in the color that I've shown, not relevant for this talk at this point. That's a desorption of a species that has formed, and you can also have desorption of your original gas molecules. So these are typical phenomena that happens for a catalytic reaction cycle. In this, if you saw, there was adsorption and desorption, and both of those is very important for catalysis as a process. And if you think about CCU, or the utilization part of it, which utilizes chemical reactions and catalysts for such processes, this adsorption and desorption becomes an integral part of the entire utilization process. Similar is the case when you have to look at separations with adsorption. You have adsorbent materials. This is a representation of porous materials like MOFs, metal organic frameworks. This is a typical representation of a flue gas kind of a mixture. You have certain percentage of CO2, N2, and probably a whole bunch of other chemicals as well. What you would typically want, you put this in, you get selectively one of the materials out. For example, nitrogen comes out, CO2 is captured, and this is a graph representing what is called as adsorbed amounts. You don't get perfect separation in most cases. Most often you do have certain amount of separations. This axis shows adsorbed amounts. More adsorbed amount means more of the material has been captured in the material. So a larger adsorbed amount of CO2, a lower adsorbed amount of nitrogen shows that there is a possibility that you can separate with these kind of materials, and this is something that is an important aspect of the capture process. So in that context, adsorption as a phenomena, or an elementary step if you want to call it, in a catalytic process is very important to understand everything else. So this particular talk is going to be based on research, but what we have learned, and we're going to talk about a few different things. One is classification of adsorption. We've heard about physisorption, chemisorption and all, and we'll see what is it that we see if we are looking at simulations. Adsorption for reactions would mean that we'll have to look at where the adsorption happens. So we'll talk about types of sites, how the substrates or whatever species is adsorbed interacts with the surface, how the site identity, the chemical identity of the site and molecular orientations impact adsorption energies, influence of co-adsorbed species, periodic trends when you move across different materials, and I'll give some examples of what we've learned with CO2 adsorption in MOF. That's what I'll try to cover in the time that I have. So to get us all on the same page, let's see, this is the way I'm going to define things, and a lot of what you are going to see on the slides will be based on these definitions. So any species that you are interested in the adsorption process, if I say that's A, and let's talk about gas phase processes, similar things can apply for liquids as well. If I say A is in the gas phase, that's being represented here, and the star here represents a site at which the adsorption happens, because adsorption is a surface phenomena. So if you don't have this place, adsorption cannot happen here. If I need to place this here, that site has to be empty. So this star represents an adsorption site. Once you have that, what you get is a result, as a result is an adsorbed species. So that's represented as an A star. This kind of a notation is very standard in catalysis. So I'm showing you a lot of catalysis representations, but it applies for adsorption as well. The reverse process is desorption, and that can be represented as what's shown in the remaining part of the slide. I'm trying to figure out how to do the navigations. I have a lot of animations. Yeah, so this is schematically represented, and what we do with the simulations is to try to get energies from these kind of transformations, and this is a typical way in which the energy is captured. The adsorption energy is the difference in energy of the species that you have, which is the adsorbed species, sorry, this one, minus the sum of energies of the individual components, both of them when they are separated. So this is what we call as the adsorption energy. If this is negative, we say that that's favorable adsorption, and in reality adsorption is expected to be releasing heat, or the reaction is supposed to be exothermic. If it's positive, you don't expect the adsorption to happen, and that's something that you don't expect to see. So this is the definition that we're going to look at. The first thing that I want to get your thoughts on is physisorption and chemisorption are two things that we have been learning from school. What's your definition of physisorption? What's your definition of chemisorption? Weak van der Waals forces? Yeah. Okay, physisorption is when you have weak interactions primarily from van der Waals forces and things like that. Okay, and what is chemisorption then? There is a strong chemical, there is a bond formation, and there is a chemical change which results. Does everybody agree to this? Okay, and that's precisely what it is, and what we are able to do is to characterize some of this with the simulations that we have. Let's take a look at this. If all of us agree to these definitions that we show, I'm showing you a lot of data here. I'll ask you to take a minute to look at it. I'll explain what the data here is. This is a CO2 molecule, okay. In the gas phase, it's a linear molecule. This is carbon, you have two oxygens. That's a 180-degree angle that you have, and the carbon oxygen bond is approximately 1.16 angstrom. Small variations are possible, and think about this, everything else apart from the CO2 that you see, as a catalyst or an adsorbent. Okay, so this is a catalyst. If you need, this is a copper catalyst. Let's say everything that you see here, I'll probably just this is also a catalyst, this is also a catalyst. Okay, so this was my linear CO2, this is a CO2, this is a CO2, and that's my CO2. Okay, and there is some information about bonds, angles, and these are the adsorption energies which are calculated using the formula that I had shown earlier. Which of these is chemisorption and which of this is physisorption? Let me just remove this off so that it's not messy. Yeah. So is this, which one is physisorption and which is chemisorption?
Sir, the last one. Minus 139.
So I'll just put this 1, 2, 3, which is physisorption, which is chemisorption.
Chemisorption is third one.
Chemisorption is 31. Okay, everybody agrees to this? Second one?
Physisorption.
Physisorption. Okay, first one? Physisorption?
First one. Sir.
There's no interaction. So
it is not forming any bond.
So this is not adsorption.
It is the initial stage basically.
What did we define chemisorption as? There is a bond formation and there is a chemical change, and physisorption was because of long range. Again, the definition of what long and short depends on what framework that you work on. Some people say it's long range, some people say it's still short range. But yeah, non-bonded interactions like van der Waals is what physisorption is primarily going to be determined by. Everybody agreed to 3 being chemisorption. Yes, you're right. What about 2 and what about 1? How many of you for chemisorption? Majority is for chemisorption, and why? Yes, I mean, I'm showing there are formation, or rather, I mean, it appears that there are bonds. If I hadn't shown those bonds, then how would you have seen it? If I had deleted that connectivity, then would you still have called it chemisorption? So what happens in a chemical process? A chemical process, like you said, there is some sort of a chemical interaction and there is possibly bonding, and bonding leads to changes in the original structure of the molecule. CO2, like I said, originally is a linear molecule. That's what you see here. Look at this particular case. The linearity is almost maintained. There is a small change in the bond distance. It is not substantial. There is a small change, and the distance from the surface is also shown. That is 3.5 angstrom. For those of you not familiar with angstrom, that is 10 to the power minus 10 of a meter. That is a very familiar unit for me, but for people who work in the industry, probably this is like, what is this, right? I was there once. I was with Indian Oil, so an angstrom was like out of range for me. Okay, but look at this particular case. You do have bond distances that are given, but what happens otherwise? You can see that there is a stark change in the chemical form of CO2. It's bent, it's not linear anymore. So even if I had not shown this bonded connectivity, what you can see is the molecule is bent. The molecule bends only when there is interaction with the surface, and that's a chemical interaction. Otherwise, CO2 is a linear species, right? So this is chemisorption, and which we can characterize by what we see pictorially, and we can also do other kinds of analysis to show that there is chemical bonding. What is characteristic of it? If you see, there is a big difference in the numbers. This is 21, this is 32, 139. That's a big difference. Everybody was very sure that this is chemisorption, possibly also guided by this large negative number. You don't expect to see physisorption with these kind of adsorption energies, but the real driving fact for you to decide if something is chemisorption or physisorption is not looking at these numbers, but rather what is happening in the interaction. So this is chemisorption because the molecule interacts with the catalyst or the surface, undergoing a chemical change, and there is that bonding that's happening. Here what you see is there isn't too much of that interaction. You can see it's relatively far, 3.5 angstrom versus 2 angstrom. That's a big difference in the molecular world, okay, and this change is minimal. That means this is very weak interactions, and what you seeing this minus 21 is a result of those van der Waals interactions and so on. Okay, so this is physisorption and this is chemisorption. So some of you rightly said the definition basically has to be the chemical nature of interaction. Whenever I teach a class, and I've done that in a few of the classes, some of them are here. I mean, I remember from my textbooks that there was a classification based on the absolute values of energy, less than 40 kilojoules being physisorption and more than 40 kilojoules being chemisorption. That's not a good definition. You really need to look at what is the nature of interactions. Okay, so this probably sets the context of what is physisorption and what is chemisorption. What we are going to see is a lot of chemisorption to go on for now, because the first part I'll focus on catalysis, where chemisorption is one of the key steps for catalytic reactions. This is a very complex.
I have a question.
Yeah.
Why was there a lot of energy difference between these two chemisorption process?
Yes, it will come up later in other slides as well. But to quickly answer the question, if you can see here, the element of interaction is copper and zinc. The element of interaction, this is zirconium and copper. So the oxygen is interacting with two different elements. In one case it's zinc, in one case is zirconium. That changes the interaction strengths quite a bit, okay, and we will see that in upcoming slides as well. So where exactly the adsorption happens really matters, and I will show that with other slides as well. So what we spoke about was physisorption, chemisorption. This is an extension of it. We will see physisorption and chemisorption here as well. The energy diagram here represents what is happening in the whole process, but I mean this side probably tells you what's happening physically. You have a hydrogen molecule that's at a distance, it's moving close to the surface and then it dissociates on the surface, okay. And what is shown here is the distance of the copper surface and the hydrogen, that's this axis. So if you move down, it's coming down onto the surface, and this distance is basically the hydrogen, or rather if this happens, if you move this way, the hydrogen molecule is splitting up, okay, that is what is being shown. And this is a color scale with the color axis like this. Large positive values shows unfavorable energies, and the lowest on this particular scale is 0, which means that is the reference. So the lowest energy is here, the lowest energy is here, okay. If you look at what is happening, there is physisorption here, which is a weak interaction. What you see is, if you trace this path this way from here, you can see the energy changes. This is becoming more than what it was when it started out here, and it ends up with something which is more negative as well. And if you trace this path, what you are going to see is molecular hydrogen kind of splitting up, and this particular configuration is completely dissociated hydrogen, and what you have at this state is 2 hydrogen atoms. So effectively you can call this dissociative adsorption of hydrogen. If you had CO2, you would have seen exactly the same thing, or any molecule for that matter. This is dissociative adsorption, and when you have dissociative adsorption, you do have chemisorption. So this is a chemisorb state, this is a physisorb state. In this case, in terms of energies, both of them are very similar, but we can capture the change, and what you see from this energy state, which is molecularly physisorbed, to this particular state, which is dissociatively adsorbed and chemisorbed, you have a rise in energy, and that particular rise in energy is what you need to be supplying for the molecule to be breaking. So if you know chemical reactions, from a reactant state to a product state, you typically go through what is called as a transition state, and that transition state comes somewhere around here. So this is a picture that captures physisorption to start, chemisorption to end, but the chemisorption was dissociative in nature, and because you have a dissociation, you also have a chemical reaction that has happened that goes through a transition state, and that is captured with this change. So the energy of the transition state from the energy of the reactant, that difference in energy is typically what is called as the activation barrier. So if you take the difference in energy here to here, that is a representation of what my activation barrier for this particular process is. But what happens is, the overall process starts off with a physisorb state ending up with a chemisorb state, and what we are able to capture in this process is also a dissociation via a transition state, which should appear somewhere around here, okay. This is also a representation of adsorption. All of that, some of the details I will skip and move on to talking about what are definitions of sites, and these definitions are very standard when it comes to catalysis, okay. Even for adsorption, we can speak about some of these kind of definitions. We will talk about it as we go ahead, but for catalysis, the process has to initiate with the molecules coming onto the surface and at specific locations, and some of the types of sites that we have are called top sites if it sits on top of an atom. Bridge site is the location that you have between two atoms. So if you take the axis connecting two atoms, the region where you have that possibility is called as a bridge site. If you have 3 atoms like this, if they are connected in a ball manner, you have this void region, which is a hollow site. That's another type of site that you have, which is called as a hollow site. And if you notice these kind of materials, there are possibilities that you can have two types of hollow sites. One, if you notice this particular case, there is a pink ball just below this, and I'll show you another case. If you take this particular case, you don't have a pink ball, you actually see another peach ball, and the way I have colored this is my first layer, this is my second layer, this is my third layer. So if you're seeing a peach ball, you're seeing the third layer. If you're seeing a purple kind of a color, you're seeing the second layer. So even as a hollow site, there are two types. The first one is called HCP hollow site and the other one is called a FCC hollow site. And these are standard sites at which adsorption can happen, and these are site types which are relevant for adsorption in catalysis. What's the difference between all of this? If you are having a top site, the number of points of contact for your adsorption is 1. So I can say the coordination number is 1 between your adsorbed species and your catalyst or surface. If you have a bridge site, the points of contact are 2 or the coordination number is 2, and if you have hollow sites, the points of contact are 3. And that is if you have this kind of a arrangement. If my atomic arrangement changes, if originally my atomic arrangement was of this kind, but instead if I have an atomic arrangement like this, if you look at this, what is happening is these are triangles, or if you want to look at slightly bigger cases, these are hexagons. Okay, this is a slightly different atomic arrangement, these are squares, and this is not exactly like very close. So these are basically different types of crystal arrangements. So this represents what is called as a 111 surface, this is a 100 surface. I'll skip all of those details. So these site types are possible here as well. So you have the top site, bridge site and the hollow site. What's the difference between the hollow here and here? This hollow is between 4 atoms, and the coordination number in that case becomes 4. Okay, so that's the difference. So there is a difference in how adsorption happens when you change your atomic arrangement on the surface. All of the atoms are of the same kind. Okay, this was a representation of copper, it can be anything. So all atoms are copper, but again depending on where exactly your molecule sits, there is a lot of differences that you see, and this will change the interaction strength or the adsorption energies that are captured. Okay. Now, when you have actual nanoparticles, things can get a little bit more complex. Everything that we saw is already possible, but you also have a few more types of sites that can be possible now. If you have a nanoparticle of this kind, it may not be very obvious, but I hope you will be able to see. This turns out to be, if I have a plane like this, another plane, the points that are in between those two planes, those are called edge atoms. So we have 3 planes, that's a corner atom, and each of them behave very differently. And if you see what is happening here, this is some sort of a stepped arrangement. There are missing atoms here, and this kind of an arrangement is called step, and each of them have their own specific characters in terms of their arrangement at these specific locations. So each of these become additional sites which can be defined for catalysis, in addition to what we spoke about in the previous slide. So you have top, bridge, hollow sites and so on, but you also have on actual nanoparticles other types of sites which are edge sites, corners. Each of them have very interesting features, because of which some of them become more relevant for catalysis and so on. Just to give you a perspective of how things change, this is hydrogen adsorption at these different types for a nanoparticle. If it's a top site, you have a value 100 or so. Bridge, very similar, but the hollow site, the value is much lower. So based on this, what we are able to say as a statement is the most favorable site for adsorption for hydrogen on platinum is my top site, because this is the most negative. Okay, doesn't mean the others don't happen, but if I am to say which is the probability by the energies, I am likely to say the probability of the site being the top site is the highest. Okay. Now if you look at the other kind of arrangement that we had, the numbers are slightly different. For the top site, that's pretty much the same. The bridge changes quite a bit. Hollow site becomes even more less favorable. Okay. So what I am trying to say is there is a lot of variability, same material, but depending on what is my atomic arrangement on the surface and depending on where exactly the adsorption is going to happen, there is going to be a lot of variation in what you are capturing. So, if you have all of this as possibilities, what you are seeing is the differences that we are looking at is 84 to 116, 30 kilojoules, and that is not a trivial number. Okay. So, these are some examples of site types. We will look at a few more cases, and this is what I was talking about, the differences that I think we were talking about to start with. This is the same example that I had shown as earlier, only thing is there are small variations. So, now can I just come back and ask, is this chemisorption or physisorption? I do not have all of the details of the bonds and the angles. What do you say? This is chemisorption or physisorption? Okay, this one? Chemisorption? This one? Chemisorption? First one? It is chemisorption. Okay. You probably would have been able to identify if I had given you more details about the structure. Okay. It is not always required that it has to bend. The bending will happen only in certain cases because of the nature of interactions, and that is what I just want to talk about. Here, if you look at this, there is only a single point of contact, and that is this one, and this atom is a zirconium atom. Okay. Here there are 2 points of contact. The oxygen is interacting with the zirconium atom and the carbon is interacting with the copper atom. Here also there are 2 points of contact. This is a zinc atom, the carbon is interacting with the copper atom. So, there is a difference, 1 point of contact, 2 points of contact. I do not have the energies written on this. This is zirconium, this is also zirconium. Where is the energy likely to be stronger? First one or second one? 1 point of contact or 2 points of contact? Where is the adsorption energy going to be higher or stronger? 2 points of contact? Everyone? Okay, you are right. 79 versus 139. The 139 you have already seen. 2 points of contact here as well. This is 32 versus 130. Now, that was the question that you were asking, and that is because of the identity, the zinc versus the zirconium. Okay. What happens in terms of the chemistry? Zinc with its atomic arrangement has a complete D shell. Zirconium is earlier in the periodic table. It is able to interact stronger with the incoming oxygen, and that changes the interaction energy quite a bit. So, if you see, the points of contact are copper, which is the same. So, the difference in energy of 100 kilojoules that you are seeing has to arise because of the point of contact with the zirconium and the zinc, and that is the kind of difference that you have with everything else remaining the same. Okay. So, if adsorption happened with all of these kind of components that you have in your material, you can see if adsorption happens in this place versus this, your adsorption energy can be different by over 100 kilojoules, and that is huge. So, that becomes very complex for you to kind of then figure out what's kind of. This is another example of a very similar kind. These are all molybdenum atoms in cyan, and this is carbon in grey, and this is a nitrogen here in blue, and the red balls are oxygen. So, this is a molybdenum carbide material. Here there are 3 points of contact actually. This is a top view. So, there is 1 point of contact here, 1 here and 1 here. Okay. This is the adsorption energy that you have. The difference here is, instead of a carbon here, this is replaced with a nitrogen, but the interaction is not on the nitrogen, it is just a neighbor, and you see 119 has become 93 despite the points of contact being exactly the same. No change in adsorption, but the presence of a hetero atom has already changed the adsorption energy quite a bit. Now, what happens if I flip it around and if my adsorption is on the other side with the nitrogen? It is 133. Now, this is why catalysis and adsorption becomes very complex and interesting. If you think about this, okay, what is the practical significance of me talking about all of this? Okay, I have been talking about a lot of numbers here and a lot of chemistry and physics, if you want to call about. What is the practical significance? When you make a material, if you know that it is a uniform single component, single element material, even in that there is going to be a lot of variability that you see if you are making an experimental measurement, An experimental measurement is going to be an average coming out of all of the variations that you are going to have for that single element. Now, if your material has even the slightest of impurities or external components, then what you are getting is again a outcome of a lot of those that are coming in as well. Even if the adsorption does not happen on the impurity, its presence, that is what this particular middle panel shows, right. Even the mere presence on the surface changes adsorption energy so much. And what I would say is catalysis and adsorption requires you to understand the surface of your material to an atomistic scale for you to be able to comprehend what is happening in the measurements that you are making. Because sometimes if you assume your metal to be perfect or material to be perfect and of a single identity without defects or without any changes the way you would anticipate as perfect materials, your assessment of what is the material underlying versus what you have in reality are going to be extremely different. So, for catalysis and adsorption, it is very important that you characterize your material to the atomistic scale to be able to know what do you have on the surface or subsurface, so that you can then try to figure out how that is impacting what you are seeing. That is the kind of outcome that I am trying to kind of show all of this for. All of this that I have shown are with very small molecules. Adsorption is not always dealing with very small molecules or atoms. When we go with slightly larger ones, things become quite more complex. Okay, everything that I spoke about until now stays valid. Now, what I am going to show is something else as well. So, this is a molecule called sulfolane. It is a solvent. It has sulfur, which is this yellow color that you have. Oxygen is in red, white balls are all hydrogen, grey is carbon, and this particular material is zirconium oxide. So, the cyan is zirconium atoms, and oxygen is. So, this is sulfolane adsorbing on zirconium atom. This is adsorbing in a slightly different way. One is vertical, one is horizontal. Where is adsorption energy going to be higher? It is adsorbing at the same site, no change. Where is adsorption energy going to be higher? Horizontal. Anybody says vertical? Everybody says horizontal. And why? If you look at it, the adsorption is through a single atom of sulfolane, which is an oxygen. That is this oxygen atom. Adsorption is happening with a single atom on the surface, that is that zirconium. That does not change here, that does not change here. So, do I expect my adsorption energies to be different? First question is, do I expect it to be different? If yes, how much? First question, the difference is of the order of 40 kilojoules, which is not trivial. And what is the difference? When it is horizontal, the molecule is able to interact as a van der Waals kind of interactions, that is non-bonded. When it is vertical, that entire species is not interacting with the surface. The interaction is only through that lone oxygen atom. So, when you have large molecules, you have a lot of these non-bonded interactions, which are also extremely critical in determining your overall adsorption strength. It is not only that point of contact. So, if your molecules are bigger, you would see the impact of this being a lot higher. One more example. I have changed from zirconium to a rhodium that is put in the same place. Okay, I have changed one zirconium atom to a rhodium atom. So, instead of this being a zirconium, this is now rhodium. Example is the same. I have changed my identity, but one is vertical, one is horizontal. What do I expect to see? Will these numbers be the same? This and this in terms of configuration are the same, but different site. This and this configurations are the same, but different site. So, we have seen in the past that if site changes, adsorption energy will change. Do you expect the trend to remain the same? Almost the same. 44 versus 41, that is a very minor change. So, sites matter, non-bonded interactions matter. Okay, adsorption is not as straightforward as you thought it was, right. Larger molecules, you see a lot more of these kind of impacts. So, we are talking about one molecule here. think of it as an experiment. An experiment is going to be not even billions of molecules, but probably even larger. All of them, if they have different orientations on the surface, one will be vertical, one is going to be horizontal, one is going to be at some angle. What you are going to see is, as an outcome, is going to be a sum total of all of those orientations put together, which could have a spread in energies if we can sit and calculate, right? But if you want to rationalize why you are getting what this is, you need to be capturing all the differences that are out there, okay? Alright, so with that I will move on to something else. All of that I have shown so far is taking a single molecule into account. In practical processes, adsorption is never going to be with a single molecule. Most often you will have multiple. So what happens if you have multiple molecules in terms of adsorption strength? So when you have multiple molecules adsorbed, what is happening? You have multiple things that are there on the surface. Originally, if there was only one molecule, only this is interacting with the surface. If I have another molecule, this is also interacting with the surface. If it is close by, then this is also going to interact. Now, it depends on the nature of these molecules that you have. If they interact positively, that is going to be an overall positive outcome. If they interact negatively or repulsively, then there is going to be a repulsive contribution that comes in, and that is what I will talk about here. So this is, let us say these are all the sites that I have, okay. If I say that I have sites which are numbered 1 to 16, and if it is possible that I can adsorb something on all of those as top sites, okay. I can count hollow also, does not matter. So I have 16 top sites. Coverage typically is dependent on or defined as how many of those sites are actually occupied with reference to what is actually available, okay. So this is 2 of those occupied out of 16. So 1 by 8 is what is called as a fractional coverage. This will be 4 out of 16, and in terms of a monolayer, it is 1 by 4. This is half, and if you have all of them, this is called as a 1 monolayer, okay. If all the sites are occupied, that is called a monolayer adsorption. Those of you who have learned adsorption and isotherm models, do you all remember Langmuir? Yeah, all kinds of adsorption models. Langmuir assumes you have a monolayer adsorption, and a monolayer would mean all the possible sites are kind of completely covered on the surface, okay. So now adsorption energy needs to be looked at in a slightly different way. Of course, you can define adsorption energy per molecule and see it as a progressive adsorption energy, or you can look at an average adsorption energy. Average adsorption energy is the same as what we had done, but you are going to average it by the number of molecules. Another way of defining adsorption energy is looking at how adsorption energy changes with every single molecule coming in and increasing the coverage. So if you look at average adsorption energy, this is some data that is there in the literature, the reference is there at the bottom. This is not our work. Most of what I had shown earlier is something that we had done in the group. So this is an example of carbon monoxide. Carbon monoxide adsorbs with carbon sitting on the metal, okay, typically vertically and most often on top sites, okay. So they have considered all possible sites, top, bridge, FCC and HCP hollow sites, which I have shown earlier. 0.25 of a monolayer would mean that you have 4 atoms on the surface, and these are representations of the pictures. And again, if you look at it, negative values, larger ones, stronger adsorption, less negative, weaker adsorption, and this is increasing coverage, going from 4 on the surface to 16 on the surface. And if you see what has happened, your adsorption energy has changed from minus 1.4 to around 0.4, and is slightly different in the case of different types of sites. But broadly speaking, strong adsorption, weak adsorption. And why? The points of contact are the same, the material is the same. What is happening? Why is this change? Earlier we had spoken about point of contact matters, orientation matters. It's all the same here. Then why is this change? Repulsive interactions. So many of the molecules, they don't like each other. There is going to be severe repulsion when you bring them close, and CO is one such. So there is going to be very severe repulsion when you bring them close, and if you see at a 0.25, there is still some sort of a separation between them. You pack them, they are very, very close to each other. So that repulsion is a big component of the total energy that is calculated, and that is something that is negative, which is being compensated by a positive repulsion, and then overall outcome is less favorable attraction, right? That's one way of thinking about it. So at an electronic scale, there are other things that happen as well, but coverage does matter, because when you say adsorption energy, and if you don't really specify the coverage, then you could be misled, because I can say my adsorption energy is 1 by 140 or 1.4 EV, okay? EV is another unit. In terms of kilojoules, that will be 100 kilojoules approximately, 96.5 to be precise. So 1.4 EV is approximately 135 kilojoules, okay? 0.4 is approximately 38 kilojoules. So the difference is almost 100 kilojoules, right? So if I say adsorption energy of CO on platinum, for example, is 140, this 140 is valid only at a coverage of 0.25. So when you have adsorption in practical scenarios, that is something that you need to kind of think about, and that's where the isosteric heat of adsorption becomes useful, because it tells you what is the heat of adsorption at specific coverages that you have, okay? And that's precisely something that we can estimate this way as well. So again, adsorption, everything apart from talking about points of contact and so on, there is a coverage impact. So if you are expecting your surface to be completely covered versus partially covered, you are going to see substantial changes in adsorption energy, and the coverage changes in practical terms typically in response to pressure. If you have a gas phase, that's what, if you have high pressure, the expectation is that you have high coverage. Low pressure, the expectation is that you have low coverage. So if your high pressure is what your experiments are, you are expecting high coverages on the surface, and your adsorption energies are going to be weak, and isosteric heats of adsorption can be low. If you have very low pressures, coverages on the surface can be low, and then your heat of adsorption can be low, high or strong. This is something again to keep in mind, that we need to be talking about coverages. But if there are heteroatoms or heteromolecules, one is of one kind versus other is of another kind, it can be completely different if they interact positively, okay? An example that I can think about, I don't have it on the slides. If you have an alcohol and water, alcohol and water interact with hydrogen bonds, okay? Individually they interact with the surface, but in between them they also can interact with hydrogen bonds. So that's favorable interaction between the molecules, favorable interaction with the surface. The sum total is not necessarily going to be repulsive that you see, but an extra compensation that comes from the favorable interactions as well. So then you need to know, are you looking at a single component adsorption, or are you looking at multiple components? And if you have multiple components, what is the impact that the individual components have with each other? That's another aspect that you need to look at. This is another thing, just to show an example again of metals and how adsorption changes. These are a bunch of metals listed at the bottom, and this is adsorption energy of 3 different species that are calculated. All of these numbers are in kilojoules per mole. So one is methane, that's up here in blue. You have CH3 and H, both of those are products of dissociation of methane. So they are individually adsorbed as CH3, individually adsorbed as hydrogen, not both of them together as I had shown earlier, okay? So what you see in orange is adsorption energy of CH3 individually on each of these metals, hydrogen individually on all of these metals. You see there is a large variation that you see here, but this line is almost flat, okay? And the variation that we are seeing, the highest, this is around 100, this is around 200. So again the difference is of the order of 100 kilojoules, which is a lot. With all of that we have discussed so far, can you tell me why there is this difference? They are adsorbed, so they are not radicals anymore, right? They were radicals if they are in the gas phase, but if it's adsorbed, they are not effectively a radical, because if they are adsorbed, it's interacting with the surface. Why do we see this difference? Sorry? No, I mean, I'm asking, why is this a flat line almost, and why is there a big variation in this? I'm not talking of individual metals. Why do you see a variation in one case versus in the other you don't? CH4 is a molecule and these are dissociated forms. It's close to 0. So what is the nature of adsorption? This is physisorption. If you look at the values, it's not absolutely 0. The scale is very, very large. So it's small negative values, but it's close to 0. So this is physisorption. These are all chemisorption. Do you expect to see a large change in adsorption energy if it is physisorption? There is no chemical interaction, so it doesn't matter what the surface is. The difference will be only with slight long range interaction variations out of polarity of the surface and so on. So the extent of variation that you are expecting to see when you have physisorption is low. So even if I hadn't shown you this, you should have been able to say if anything physisorbs, the trends across different materials are almost going to be flat. You will see a difference when you have chemisorption because you have chemical bonds and the chemical identities do make an impact. That's what I have shown you earlier. And again, different metals have very, very different trends. And if you look at these values towards the right versus these metals, there is a difference. Where exactly are these metals on the periodic table? Copper, silver, gold. What's peculiar about them? They are all towards the right of the periodic table. If you look at the transition metals, these are called coinage metals. The reason coins were made out of them was that they are relatively inert. Of course, silver kind of does get a little bit of a coating and so on, but typically they are very unreactive in their bulk forms. Gold is jewelry material because it is not supposed to react in the bulk form, right? Of course, nano gold is a very different case. So these are relatively weak interacting materials in their bulk form. Anything that is to the left of the periodic table where you have unfilled d orbitals are the ones that are likely to be stronger in terms of their ability to interact. So that's what we see, and these are the active catalysts as well. Anything that is able to adsorb properly will actively adsorb. So these are some trends to keep in mind again. So that's where all the active metals lie: copper, zinc, gold, and zinc, copper, silver, gold, and the zinc, cadmium, mercury. Usually you don't look at, but zinc is there. So I had examples of zinc that I had shown earlier. So these are inactive ones, and the rest of them are the active metals. Okay, so moving on, talk a little bit about adsorption and then adsorption in gas phase as adsorption as a process, and these are examples of MOFs. Is everyone familiar with MOFs? Metal organic framework. Metal organic frameworks. Okay, for those of you who are not familiar, typically there is a metal. There are various possible metals that are possible, and then you have organic ligands, and they come together to form certain networks, and they will form crystalline networks, and these are called metal organic frameworks. So if you change the metal and if you change the linkers, you can make literally millions of them, and I think millions have already been made or at least predicted. The example that I am showing you is one particular MOF, and it's called ZIF 90, and ZIF stands for zeolitic imidazolate framework. Okay, it is a class of MOF. It has a zeolite like structure, so that's why it's called zeolitic imidazolate framework, and the linker that is used is based on imidazole, which is one of the organic molecules, and this is imidazole carboxaldehyde, and that's why it's called ICA. You have a CHO group here, and the rest of it is basically the imidazole backbone, okay. And you have in this particular material zinc as the metal. Of course, like I said, various kinds of these materials can be made, and this is a representation of what is called as a unit cell of this material. It has a cubic shape, it forms a cage, okay. These are porous materials like this, imagine. So, you have a big cage and these cages can hold molecules, okay. Because of this, these are extremely useful as adsorbent materials. They have a large surface area for adsorption and these cages are available. So, overall when multiple of these cages come together, you can put together, it is a large porous material, lot of pore volume where adsorption can happen, okay. That is the nature of these material, and I am just showing you some data. Again, the molecules that are seen here, this is CO2, this is CO2, this is CO2, again this is CO2 here, this is CO2 here. With whatever we have discussed so far, do you think this is chemisorption or physisorption? There are some distances given there as well. Anyone who thinks chemisorption? Anyone who is tilted towards physisorption? Physisorption? This is physisorption, okay. If you look at it very carefully, I mean the first and the second images, let me just delete the markings. Not sure if you are all able to see the distances. They are all of the order of 4 angstrom plus. At a molecular scale, that is pretty large, okay. And it may not be very obvious, the linear shape is almost held as well. I mean we can do analysis and show it is not changing so much. All of this is physisorption, okay. So, the way most of adsorption that happens in many of these materials, if they are perfect, is by physisorption, okay. If there are defects, and defects I will not be talking about for now, defects could be metal sites where the linker is not coordinated, okay. So, these metals are basically coordinated with 4 linkers in this particular case. There is no place for interaction with that particular metal site. So, the linker is 4 coordinated in this. In that case, there is absolutely no way there is a chemisorption that is possible. So, the interaction here primarily is physisorption, but even within physisorption, okay, what you see here is this is one view where there is a 6-membered cage of sorts, this is a 4-membered cage of sorts, and both of them have both kind of a going into the cage kind of an orientation and some sort of parallel orientation. If you see, the energy changes not a lot, but there is a change in energy. The highest that we have here is around 31 and the lowest we have here is 16. All of this is physisorption, that is the amount of change that we can anticipate, not more than this. And where exactly do you see the adsorption happening? These are all the linkers. The adsorption is not happening with the metals, but it is because of the linker. Now, if you know this, if you need to design materials, now what do you need to do? You do not need to change your metal, you basically need to figure out what are organic linkers that can interact stronger with your CO2. What functional groups in your linkers will change the adsorption? I do not have it on the slide. So, you have a CHO group here. There is another ZIF which is called ZIF 8 which has a CH3 instead of this. If you have that, the strongest adsorption is only around 20 kilojoules instead of the 30. So, that one CH3 instead of the CHO has changed the adsorption by around 10 kilojoules, and this has an impact, okay. I do not think I have a comparison on the slides, and these are adsorption isotherms. You can do this in experiments, you can do this with simulations. In simulations, this is done with what are called grand canonical Monte Carlo simulations. So, what you are seeing is pressure on the x-axis, adsorbed amounts in millimoles per gram of the material on the y-axis. I will let you take a look at this for a couple of minutes. What you are seeing here is not an impact of a single molecule adsorption. Okay, like I said some time back, pressure matters. High pressure, more species interacting. Low pressures, low species interacting. So if you have more species interacting, of course capacity is also going to be changing. So this is not interaction strength like I had spoken about earlier, this is capacity. Okay, so if you increase pressure, what you see is capacity increases or the adsorbed amounts increase, and that's naturally expected. That's what your adsorption isotherms show, right? So this trend of it being kind of increasing and then kind of tapering off is not something which is unexpected. What was the temperature impact? Adsorption, like I said to start with, is expected to be an exothermic process. If you have higher temperatures, adsorption is going to be very severely impacted. So if you look at the first, this is 10 degrees, this is cold for process, you can do it in lab, but replicating 10 degrees in an environment, yes, you need cooling to get there, versus 60 degrees, which is probably for the temperature for most of the flue gases and so on, even after a certain length of the stack. You see the difference in capacity, that's quite a lot. So temperature has a very big impact. All of what we had spoken about, we did not talk about temperatures to start with in all the previous cases. Now what I am showing here in practical case is temperature does matter, pressure does matter, sites do matter, adsorption is very, very complex. Okay, and I'll stop it at that. I don't think I have any more.